right, so we're going to have our second talk for the last day of the Categorical Probability and Statistics workshop. And the speaker during this hour is Bart Jacobs, and he'll be talking about Finetti's construction as a categorical limit.
Okay, thank you very much. Thanks for joining, and thanks to the organizers for making this happening after all. I'm going to talk today about the Finetti's construction, which is a classical resultant probability theory going back to the 1930s, which I'll describe in categorical terms. And this is joint work with Sam Staten from Oxford, who's been talking earlier at this workshop. So this is an outline of my talk. It covers multi-sets, distributions, channels, and also some coalgebra. As I'll mention at the end, this is originally a submission to the coalgebra workshop. A very familiar example in probability theory is Polya's urn. It is an urn which may contain two colors of balls, black and white. Let's assume we have B black ones and W white ones. The mechanism is you draw a ball, you note, you write down its color, and you replace the ball and add an extra one of the same color. And you do this multiple times. In a standard description of this urn, you get a sequence, an infinite sequence of binary random variables, which are either 0 or 1, and 0 if you draw a white one, and 1 if you draw a black one. And as you can imagine, because you add balls at each step, the probability distributions involved become quite interesting. Let's write P of n for the joint distribution of the first n random variables, and then there is an important property that these joint distributions have, that is exchangeability. That means that their value is independent of the permutation of the order of the variables involved. So here's an example for at level 5. If I have 2 1s and 3 0s, so that means if I have drawn 2 black balls and 3 white ones, the probability I get doesn't depend on the order in which I drew these balls. This is very remarkable. Now in this context, there is the famous theorem of the Finetti in binary form. And it says for this infinite sequence of random variables can be described, or at least the underlying joint distribution can be described via a unique continuous measure on the unit interval 0, 1 via this formula, in which you may recognize binomial probability, and that will be one of the themes involved. And we use in here the powers x to the power t, where t is the sum of these variables x, y. So it's the total number of black balls that was drawn. So the actual order doesn't matter, but the total numbers matter. And this is important, and is already pointing at the existence of a multiset in here. So what is the approach and the insights and the contributions underlying this approach? First of all, an evolutionary, but it's a basic starting point of our approach. I'll come to multisets in a minute. Drawing from such an urn can be described as a coalgebra, actually as a channel, as I will also say, which acts on these multisets. And iterated drawing yields a distribution on multisets. So we're now putting structure on top of each other, distributions on multisets of colored balls. And as I emphasized already, the total number t of the drawn balls is relevant, not their order. And this points in the direction of using multisets here. Because indeed a multiset is a structure in which you can collect elements in which the order doesn't matter, but the multiplicity of elements is relevant. So in comparison, in a list, the order does matter, and in a subset, the order does not matter, and also the multiplicity of elements does not matter. These distributions of multisets, they form actually a cone for an infinite chain. And here we're going to move into the direction of a limit structure. And the chain and the cone live in a Kleisli category. So here some monad structure is appearing. And the Finetti's distribution mu that I had on the previous slide arises because the unit interval 0, 1 is the limit of this coin. So actually, this is the heart of the matter, that Finetti's statement is actually a limit statement in a suitable Kleisli category. And the Finetti has had a lot of impact because it describes some fundamental property in probability theory, which can be described informally as if you have a consistent sequence of discrete distributions, there is an underlying continuous, even unique underlying continuous distribution. And here we'll formulate this as a diagram in the Kleisli category of the discrete distribution monad has a limit. If we move this category to the Kleisli category of the Giry monad, where you have more structure and where you can talk about infinite aspects and continuous distribution. So this gives an overview of the talk, and now I'll go into more details. By the way, feel free to interrupt at any time. I'm happy to take questions during the talk. Multiset. So multiset is a set, sometimes called a bag in computer science, is a set in which elements may occur multiple times. And I'll use a formal sum notation for multisets. I will only look at finite multisets, so with finite many elements. So I'll use a formal sum notation with these get brackets here, and they are used to distinguish the elements from the of the multisets from their multiplicity. So in this example here, I have a color mix where I have 3 units of red, 5 units of green, and 2 units of blue put together. But at the same time, you can see this as an urn and a container which contains, let's say, 3 red balls, 5 green balls, and 2 blue balls. So a multiset is a very natural container construction describing basic models used in probability. Now, multisets can also be described as functions with finite support, and I will switch back and forth between the description as a formal sum or as such a function description. So the multiset is on X with element from X. It's a function from X to the natural numbers, describing how often this an element from a set X occurs. And this is actually functorial. If I have a function f from X to Y, I get a function between the corresponding multisets, which can be described in this way simply by applying a function to the inside the cats. Okay, furthermore, this M is a monad on sets, but I will not really use that in my talk. Another thing which I will not really use, but it's good to remember or to know, is that M of X is a free commutative monoid on a set X. Addition of multisets is pointwise. You just add elements, the multiplicities of elements together, and the empty multiset is simply with each element occurring 0 times, and that's the 0 element for this monoid structure. I'll write M star of X for this subset of non-empty multisets. So it's the support is non-empty and finite, or if you like, the sum of the multiplicity is bigger than 0. And actually the non-empty multisets form a submonad, but that doesn't matter too much. So for each number k, I write M square brackets k of X for the multisets over X which have precisely k elements in total. So the sum of multiplicities is k. And let's see an example again. This red, green, blue It has 10 elements, you just add them up. So it's in the M of 10 of the set RGB. The notation may become a little bit heavy, but at least in such a concrete example, it's clear what's going on. Good. So we know multisets. Let's look at distributions. They're rather similar. Finite discrete probability distribution is a convex combination of finitely many elements. I will also use a convex, a formal sum notation with these cats, but now the multiplicities are numbers from the unit interval 0, 1, which add up to. So we get a convex sum of these elements. And I also sometimes call them a state, a distribution state. Some of this work and also notation is inspired by quantum probability, where distributions are called states. And an interesting observation, if I take distributions over the 2-element sets, that's the unit element. So the distribution function maps Booleans to probabilities, if you like. Again, this is a monad. I will use the terminology channel for a Kleisli map of this monad, and I'll use a special arrow notation for it with such a circle on it. So again, I'll switch back and forth very easily between a channel and this. The function notation and the channel notation. And one of the important things you can do with such a channel is do state transformation, for which I'll use these double forward notation, which might be a little bit confusing if you use Haskell's bind notation, because the F and the omega are used differently, but it's a push forward measure. The idea of pushing omega forward is expressed in this notation. Good. Let's see how this works. So let's look at binomial distribution. So suppose you want to do a number of trials, and each trial has a probability R of success. And the binomial distribution describes the probability of getting small k out of big K successes. I will describe it as a channel here. So as a capital K I will use as a parameter, and it's a channel from 0, 1, that's the trial probability, to the set of outcomes 0, 1 up to K, namely the number of successes. So the binomial K of R here, it's a formal sum over all the small k's, and the small k's appear here then as this in this cat, and this is the typical probability that's associated with the binomial. So it's a channel in this sense, which is a probabilistic function from a probability to. Okay. Interesting observation is that K successes out of big K can be described as a multiset. Namely, if I associate 1 with success, I can say K times 1 plus capital K minus small k times 0 is for the failures. So small k successes is a multiset over of size capital K. Actually, there's an isomorphism. The numbers 0 up to K can be identified with such a multiset with capital K elements over 0, 1. Now, this may look like a bit of a formality, but the way I'm describing, the reason why I'm emphasizing this is that with this notation, I can describe the binomial channel is going from D of 2 to M of 2, the multisets over 2, but multisets of size K. And notice it's a channel, it's an arrow with a number on it. And this formulation opens the perspective of describing multinomial distributions. Because in the binomial case, a trial has 2 outcomes. In the multinomial case, you want to look at trials with multiple outcomes. Now, what is the way to describe this in a channel perspective? It's actually rather clean. It's a channel from distributions on X to multisets on X of size K. So if that means you do a multinomial distribution with a total number of capital K trials, but you can do the trials in each of the possible outcomes. Now, the explicit description of this channel involves quite some notation. I'll try to explain it slowly. It doesn't matter too much if you don't get all the details at once, but the main idea is probably useful. So the multinomial of K, it acts on a distribution, which is a formal convex sum of elements. And it becomes a very big expression, which is a distribution over multisets. And the multisets are given here. So they are in a big cat, a big outside cat, which contains inside a multiset. And this is the probability of this multiset. And if you've seen these things before, you'll probably recognize the probabilities here, the structure here. But the important thing here is that it can be described in a very structural and smooth way. And this is what I need in order to set up a cone later on.
So I just have a question, just to maybe keep an example in mind besides the coin toss. If I have like a 6-sided die, then what this is saying is like, if I roll it a certain number of times, then this is describing the probability of having like 1s, 2s, 3s, 4s, and 5s, and 6s. Okay, thank you.
So if you have a 6-sided die, then X, your set X consists of the elements 1 to 6. Those are the possible outcomes. And then the small ki's are the multiplicities of, so K of 1 is the number of times you get a 1. The K2 is the number of times you get 2. And this gives a multiset. And you assign a probability to the multiset of getting so many times these outcomes. So it's really structure on top of structure, but once you get into this, it starts becoming reasonably natural to do it like this. But I understand the notation can be overwhelming at first and maybe a bit too formalistic, but it does make sense, and hopefully you'll see the benefit in a minute. I'll also need a little bit of continuous probability theory. So for a measurable space, a distribution is a countably additive map, as we all know. We'll write G of X for the set of such continuous distributions. It forms a monad, a Giry monad. It includes the discrete distribution on a set. And this inclusion gives an inclusion of Kleisli categories. And actually, I only need continuous distributions on the unit interval 0, 1, so I will not spend too much time on that. Okay, channels and cones of channels. Now let's start drawing from an urn. So suppose I have an urn which contains K items in total. So out of a set of elements X. So it's a multiset of size K, multisets of size K over X. And drawing and deleting one element yields a channel, namely from multisets with K plus 1 elements to it gives a distribution over multisets with K elements. I'll give the formal definition, and then I'll give an example which will make it a bit clearer. So if I have a multiset phi with K plus 1 elements, it is turned into a formal sum over multisets with 1 element removed. And then the probability is precisely how many times elements. Okay, let's see an example. So if I draw and delete from this multiset 3, 5, 2 of red, green, and blue, I can draw a red one, a green one, or a blue one. What's the probability that I draw a red one? Well, in total, I have 10 elements. So the probability of drawing a red one is 3/10. And if I draw the red one, the number of red elements is reduced by 1. I can also draw a green one. The probability of doing that is 5/10. And then I reduce the number of green ones from 5 to 4. I can also draw a blue one. The probability is 2/10. And then I reduce the number of blue ones. So it's a rather straightforward mechanism that I follow here, which really can be described nicely via the combination of multisets and distribution. And actually, I will be interested in the infinite diagram of channels going backwards, where each time I draw and delete one element. So I have two elements, and I draw and delete, I get one, etc., etc. Good. And a very basic fact is that multinomials form a cone for this diagram. And so if I take multinomial distribution, which remember is a channel from distributions of X to multisets with K plus 1 elements, I draw and delete. The channel I get is multinomials where I do K experiments in total. And this is a very, very basic relation between very elementary operations in probability theory. The proof of this result is a matter of 5-6 lines, and it's basically unpacking the relevant definition. So it's Kleisli composition, and it's really crucial here that we use Kleisli composition. So really the monad structure is deeply embedded in the structure here, the interplay between distributions, multisets, and multisets, and the operations. So I would say this is a very, very fundamental fact that you have a cone of this form, and it shows it displays some well, maybe deep, well, elementary, let's say elementary categorical structure and probability. Now, how can we reformulate now the Finetti's theorem? It says that if I take x of 2, this diagram is a limit. This for x is 2, this is a limit. Now remember, on the previous slide, I had d of x here, but if I take x is 2, d of 2 is the unit interval 0, 1 everywhere, and the draw and delete maps each time take one element from this set. So this is a limit. Again, this is, I think, a very, very fundamental result. Again, of course, it goes back to the Finetti, but it's the fact that it can be reformulated categorically like this is also says something deep. A subtle point is in which category precisely is this a limit? This diagram, this cone, lives totally in the Kleisli category of the discrete probability monad. Everything is discrete here. But as soon as we want to take a limit, we need to include continuous probability, so we have to embed this original diagram in a richer category, the Kleisli category of the Giry monad, and there we can formulate it in this way. Okay, how does the proof work? The proof is actually not completely trivial. It uses Hausdorff's moments theorem that a continuous measure on 0, 1 is completely determined by its moments, and these moments, they form a so-called completely monotone sequence. And the essence of the proof is showing that this cone property is related to gives rise to a sequence that's completely monotone. And for this, for the details, I refer to a paper which I'll mention at the end of my talk. I don't want to go into the proof now, but because usually giving a technical proof in the talk is not a good idea. So let's go back to Polya's urn example. So the urn, remember I wrote B for the number of black balls and W for the number of white balls, is a multiset. in M over 2. We assume it's empty, and I can describe the draw and recording map as a channel. It takes such an urn, and if I draw k times, I get k balls out of it, which are either 0 or 1, which gives me a multiset over 2. Namely, the number of balls I've drawn. This is a channel, and it describes precisely the probability of it. There's a formula for this channel, which I will skip now. The important thing is these channels, they form a cone for this draw and delete diagram. By the Finetti, this gives a mediating map. By the Finetti, in this limit form, it gives a mediating map because 0, 1 is the limit cone. It's a limit cone in the Kleisli category of the Giry monad. So it's the mediating map is a Kleisli map for the Giry monad, which I've written here with G explicit without a circle on the arrow. But if I do write it as with a circle on the arrow, it's the beta channel. It's a very well-known distribution, which you can describe in the following way, very formally as a channel. Beta on such a multiset, the elements B and W are, I hope you recognize, commonly denoted as the parameters alpha and beta of the multiset M. You take the integral over this construction, where here this fraction below the line is a normalizing fraction, which I will not go into. Now this factorization of Polya in terms of this beta channel, it's well known. What is new, our observation that it arises as a mediating map for a limit for such a cone.
Sorry, I had a small question. What was the difference between M lower star 2 and D of 2?
So M of 2 are multisets over 2. So so that means I can have 5 times 1 and 3 times 0.
Right, they were
E of 2 are the distributions where you need convex sums.
Okay, thank you.
Right?
Yes, yes.
Yeah, it can be a bit confusing, of course, so because the interplay between multisets and distributions is very, very fundamental between in what's going on here, and it's good to keep track of what is what at which stage. But once you do that, you do get a smooth description in terms of these channels. So there's an alternative coalgebra formulation for this. So what is a coalgebra for an endofunctor? So a functor from a category C to itself is a map C from X to f of X. And a homomorphism of coalgebras is a map between the underlying objects giving such a commuting square. And we are interested in very special coalgebras of this form from X to D of 2 times X. So the functor f is distribution over 2 times blank. We're calling such a coalgebra exchangeable if this diagram commutes. This is a diagram of channels. That's why I wrote the tensor here for putting the identity in parallel with the coalgebra C. But the important aspect of exchangeability is that these outcomes on 2 can be exchanged. So if I do the coalgebra twice, so I get 2 outcomes in 2, and it doesn't matter in which order they occur. This is the aspect of exchangeability, which you may remember was one of the assumptions in the original formulation of the Finetti's theorem. Interestingly, the Polya setting can be described as such a coalgebra. Now, how does it work? Well, again, I start from a multiset with B black balls and W white balls. And I have to give a distribution over 2 times, again, a multiset. So here, this first component gives the element I draw, which can be a 1 or a 0. If I draw a 1, that is done with probability B divided by the total number of balls, B divided by B plus W. And here it's W divided by B plus W. And remember, the way this Polya urn works. If I draw an element, I register its color, I put the element back and an additional element of the same color. So here I draw a black one and I increase the number of black balls in the urn by 1. Here I draw a white ball and I increase the number of white balls. Okay, a lot of notation, but it makes sense to describe things in this way to capture the situation. Interestingly, this coalgebra is exchangeable. And this is fundamental in the Polya situation. This exchangeability can now also be expressed in terms of the coalgebra involved. Okay, let's switch back to the general level. Suppose I have such a coalgebra x to t 2 times x, now described as a channel. There's implicitly a distribution here involved. I look at the k-time iteration obtained in this way. I do C, I do identity times C, so C again on X, I get 2 times 2 times X. I do this multiple times and K times until I arrive here at 2 to the power K times X. I throw away the state. And if I have a sequence of K elements of 0, 1, I can turn this into a multiset simply by counting. And it's precisely at this point that I throw away the order. So this is a list which still has a specific order, and here the order is thrown away. And again, these maps CK from X to multisets of K over 2 form a cone for this draw and delete chain that I described earlier. The Finetti in this limit form now gives a unique mediating map over line C from X to 0, 1, because that is the limit, yeah. I got a bit confused because I forgot to put a circle on this map. In terms of finality, there is a Bernoulli coalgebra, a very, very simple one. On the unit interval, I can put such a coalgebra. It sends a probability R to the convex combination R times, I draw a 1 and I keep the same probability, or 1 minus R, I keep a 0, and I get a 0 and keep the same probability. And this coalgebra is also exchangeable. Now, what is the main result? Saying that the Bernoulli coalgebra is the final exchangeable coalgebra. So the map C overline that I got in the previous slide is a coalgebra in this sense. And now I notice that I also mixed things up in this diagram. I should have described this in terms of channels. Then it's really a coalgebra. So sorry about that. Okay, this brings me to my conclusion. One slide. First of all, the main contribution is that this work gives a new and modern perspective, a categorical perspective, I would say, on an old classical result from the 1930s. And maybe this could be useful in axiomatic or synthetic approaches to probability, for which there's much attention here at this workshop. As I said, the paper has been accepted for CMCS, coalgebra methods in computer science. The workshop never materialized, but the paper is on the archive. Please have a look there if you want to check out the details. One of the main points of the paper is that the interaction between multisets and distributions is essential in basic probability theory. Look at when you have an urn, often in the beginning of when you start learning probability theory, many of your examples come from a setting of an urn where you draw balls, but actually also in learning the interaction between multisets and distribution is very important, because your data can often be described as a multiset, possibly a multi-dimensional multiset when you have a table where you have so many elements occurring in different positions at the table. That's simply a multiset over, let's say, x cross y. And from such a table, you can derive a distribution in various ways, either in a frequentist way or in a Bayesian way. And this is one of the topics I've been interested in lately. Also, what I like to emphasize is that this channel-based perspective is very useful. It's becoming more and more popular, also, for instance, in terms of Markov categories, as Tobias Fritz is trying to axiomatize, where these kind of things can be expressed. I've been working also using these channels in Bayesian networks and logic, and conjugate priors, etc., which are, for instance, conjugate priors is a difficult notion to understand precisely what's going on, but in terms of channels, you can give a very precise description of what's happening here. Now, an obvious question is, you've done the Finetti for x is 2, for the binary case. Can you generalize? We have not done this. Sam Staten and I have not done this, but we are aware of possibilities. There is, remember the proof we used Hausdorff's moments theorem in binary form. There is also some work on multivariate versions of this result, and we might be able to use that to generalize the Finetti, at least to the finite case. For a more general version, we could look at using Polish spaces, and there is some work in this direction by the authors listed here, Dahlquist, Dano, and Garnier in Conqueror 16. This concludes my talk. Thanks for your attention. I'm happy to take questions now.
All right, let's thank Bart Jacobs for an excellent talk.
Thanks.
Feel free to ask questions. I might as well start because I actually had one about the very last thing you mentioned with the multivariate Hausdorff moments.
Yep.
In the diagram you gave, you described how d of x was actually a cone for the diagram that you gave. And then you showed, well, when x is 2, then d of x is the interval. So then that cone is actually a limit. And I was immediately curious what happens when x is 3 or something like that. And I don't know too much about this multivariate Hausdorff moments, but is that exactly the question that you're referring to? When x is larger than 2, you don't know what happens?
Yeah, that's what.
Okay.
Yeah, that's what this paper is about. I've only looked at it diagonally. It's my impression is that the matter is not completely solved in this area. So JMA, the title of the journal is Journal of Multivariate Analysis. This is an area in itself, and we really have to sit down and look at the details to understand precisely what's going on there. So I think what they do there is useful for this. I also have some confidence. I mean, this theory looks so beautiful, it must be right. if you know this, so sometimes you look at certain formalizations and you know, yeah, this is how it should be. And I have the similar feeling in this case as well. And so I would even dare to say, if it's not in that paper, if it's not being done there, then there should be a version of multivariate Hausdorff moments which makes this generalization possible.
I see. Excellent. Thank you. We have a question from David Spivak.
Yeah, thanks. Great talk, Bart. This was really cool. Can you just take me through the result that, so you said there's a cone with distributions back maybe 1/3 or so through the talk, or 40%, I don't know. And yeah, that around there, but maybe, yeah. But the cone itself and in pink, And just the commutativity, can you talk through the commutativity in the Kleisli category? Can you move back one slide or something?
Commutativity in the Kleisli category?
The fact that it is a cone.
Oh yeah, that's this statement.
That thing, yeah.
Yeah.
Can you say this why one diagram there commutes just like slowly in terms of Kleisli categories?
No, it's really a detailed calculation. Please have a look at the paper for that.
It doesn't have any intuitive.
Like this, you really have to unpack. I cannot give a clear intuition for this.
Okay, thanks.
But the idea was roughly that, right? Like if you take this example of a die and you like paint distributions on it, then this multinomial tells you how many times you're going to get this or that, and then delete and what did the D stand for? Delete and
draw and delete.
Yeah, exactly. And then you could probably work it out from the statistics. But I guess, David, you were asking a more conceptual thing about it.
Yeah,
just some kind of way of understanding. I mean, I somehow this looks like either it's obvious or it's amazing, and I think to me it's more on the amazing side. But I think if I understood better, I would think it was obvious or something. I don't know.
And I think it can be both. You agree?
Could be. Not for me yet.
No, but it does give some really basic facts. Yeah, that if you do experiments and you delete from the results that you get, you delete one element. You could have done the same experiment with fewer trials. So it's a certain consistency of doing trials and deletion.
Yeah. But if you didn't delete, I see. Well, then it would be different. Okay. Yeah.
Yeah.
Okay. Thanks.
I have a question. So thanks for a really nice talk. I'm curious, you mentioned a few times that this interplay between multisets and probability was fundamental. So I'm not an expert. Does there exist a pre-existing literature on this interplay, or are you sort of introducing multisets into the analysis of probability theory? That's the first question. And then the second one is that it just seemed to me that this multiset formalism might also be particularly useful in talking about bosonic statistics and quantum theory, given that, and so that's the second question, whether you've thought at all about that.
Now, but the second question can be short. I haven't thought about that. That will be very interesting, very fascinating. I'm not aware of pre-existing literature. I'm coming to the first question now, but I think it has been somehow in the air. But I think I dare to claim that I'm maybe the first one who's systematically exploiting this and writing this down. For instance, I have a recent result also that gives a derivation of the hypergeometric distribution, which is a very fundamental distribution about drawing things multiple times and then gives rise to a distribution. So iterative drawing. Now the hypergeometric distribution can be obtained by doing this iteration in the Kleisli category. So then the formula sort of arises from the Kleisli composition by itself. And I think that again shows that there's a deep interplay or elementary interplay between Kleisli structure and probability.
Okay, thanks.
Yeah.
Do we have any other questions? I might have a small question, although, well, okay, Gordon Plotkin has a question.
Yeah, it's a very big question, so I may not have any answer. But with all these combinatorial formulas, to handle them categorically, there's the idea of using the theory of species. You think there could be any kind of combination, kind of grand combination?
Yeah, possibly. Yeah, I don't have an immediate answer for me. So I've been concentrating mostly on using distributions and probabilities on these, and that already works well. Maybe I should generalize at some stage, but so far I'm still getting results here.
No, it's just you're doing all these calculations and they may come out by additional categorical machinery. That's what I was wondering.
Yeah. I'll look into it, Gordon. Thanks for the suggestion.
Thanks for doing the work.
Yeah, okay. Nice talking to you. By the way, I should credit Sam for this. It's really joint work, and we had basic ideas and that fitted together very well.
Yeah.
So I have another question. I'm curious whether these sorts of techniques might be useful for analyzing results that go under the name of finite definity theorems. So if you're not in the limit, but you've got some finite sample, you can sort of get corrections to the Definetti form and sort of bound how far you are from the Definetti form. It feels like this might be a useful approach to that.
Yeah, could very well be. We have not covered the whole landscape because Definetti is a topic and an area in itself. We've certainly not tried to cover that completely. As I told, we already got stuck after the binary case, but still we think we have an elementary useful result that can be used as a sort of, can give leverage to open up a new perspective on these kind of things. And indeed, it was already mentioned that there might be connections with quantum theory. And I'm deliberately using this terminology of channels because that's also used in the quantum setting, and I've used this diagrammatic notation. But again, this can be reformulated in terms of string diagrams, if you like, and then the results can in principle also be formulated in a quantum setting. Whether they hold or not there is then a next question.
There is a quantum Definetti theorem, so that's
Yeah,
another.
I see. Yeah.
There's another useful possibility there for trying to see if you could get a kind of unified proof of the two Definetti theorems.
Yeah. Very good. Yeah. But
Thanks.
Again, this is a starting point.
Yeah.
All good suggestions, and maybe I can still work for a year or two on this. Yeah. Or maybe someone else can.
Any other questions? All right, if not, then let's thank Bart Jacobs again for an excellent talk. All right, so this, I think, concludes the last day's first session of the Categorical Probability Conference.